September 23, 1999. High above Mars, a spacecraft is about to fire its main engine for the last time. It has flown for 9 months, 286 days, alone across interplanetary space. It has done everything it was asked to do. In a control room in California, the navigation team listens to its radio tone. The burn begins on time. The tone holds steady. 4 minutes and 6 seconds into the burn, the tone stops. 49 seconds earlier than predicted. It never comes back. The spacecraft was healthy. The engine performed. The number that killed it had been sitting in a file on Earth for 9 months, and for weeks, people had sensed something was wrong. Case file number 2. Mars Climate Orbiter. No one dies in this case file. What is lost is a spacecraft worth $327 million and something else. The idea that seeing a problem is the same as stopping it. The 1990s. NASA is under orders to do more with less. Faster, better, cheaper. Smaller teams, tighter budgets, shorter schedules. Mars Climate Orbiter is built to study the weather of another world. It will map dust and water vapor and listen for the climate history of Mars. It has a second job. In 10 weeks, a sister ship called Mars Polar Lander will arrive. The orbiter is its radio relay, its lifeline home. The spacecraft is built in Colorado by Lockheed Martin. It is flown from California by the Jet Propulsion Laboratory, the team that has navigated every Mars mission for a generation. 2 teams, 2 states, 2 cultures, and between them, 1 interface. On 11 December 1998, the orbiter leaves Earth on a column of fire. The cruise is quiet, almost. Here is the problem with flying to Mars. You cannot see the spacecraft. No telescope on Earth can find something the size of a car at that distance. So how do you steer it? Navigation is done by radio. The spacecraft transmits a tone. As it moves, the tone shifts. From that shift, the team measures its speed to a fraction of a millimeter per second. But that is only one direction. The rest is mathematics. A model of every force touching the spacecraft. The pull of the sun, the pull of the planets, and every breath of its own thrusters. Which brings us to a quirk in the spacecraft's body, not a defect, a design choice. Most spacecraft carry 2 solar panels, balanced like wings. This one carries a single large array on one side only. It saved money. It also made the spacecraft lopsided. Sunlight has pressure. It pushes on that one great panel, day after day, patiently trying to twist the spacecraft around. Inside, spinning wheels absorb the twist and hold the craft steady. But the wheels can only spin so fast. Every day or so, they fill up. So the thrusters fire, briefly, to unload them. A routine housekeeping event. A tiny puff of gas and a tiny shove pushing the spacecraft off its path. The lopsided design means these events happen 10 times more often than planned. Tiny shove after tiny shove after tiny shove. Each shove must be added to the model. The spacecraft radios down what its thrusters did. On the ground, a piece of software turns that telemetry into numbers the navigators can use. The software is called Small Forces. Remember the name. This entire case lives inside it. The interface between builder and navigator is governed by a written specification. It states plainly that thruster impulse shall be delivered in metric units, Newton seconds. The contractor's code delivers pound force seconds. Imperial, the old measure, off from metric by a factor of 4.45. The navigation software does not know that. A file has no accent. The numbers arrive naked, and the model reads them as Newton seconds. so every thruster event enters the model at less than a quarter of its true size. The spacecraft is being shoved 4.5 times harder than its navigators believe. No test ever compares the file against the specification. The check that would have caught it in an afternoon is never run. And there is a warning right at the start. For the first months of the cruise, the file format is broken and the data will not load at all. The fix is rushed in. The units are never questioned. Now watch the error breathe. Every unload of the wheels, a shove enters the model at a quarter strength. The modeled spacecraft and the real spacecraft begin to drift apart. The drift is sideways, across the line of sight, the one direction the radio tone struggles to see. Millimeters at first, then kilometers. The navigators cannot see the spacecraft, but they can see their own solutions. And the solutions do not agree. Different arcs of data give different answers. The disagreement is small, persistent, and wrong in a way nobody can name. It nags. At the working level, people notice. Concerns move by email, by corridor conversation, by a note at the end of a meeting. The project has a formal process for exactly this. An anomaly report, a form that, once filed, cannot be ignored. It forces investigation. It forces an answer. The form is never filed. The concern stays informal. And informal concerns can be politely, reasonably, endlessly deferred. Meanwhile, the team is stretched thin. Faster, better, cheaper. The navigators are flying 3 missions at once. Nobody has slack to chase a nagging feeling. Early September. The 4th course correction burn. The aim point is set for a first pass 226 kilometers above Mars. Comfortable. Safe. In the final week, the solutions start to slide. 170 kilometers. 150. Every new answer is lower than the last. There is a 5th correction burn on the books, a contingency for exactly this moment. It has never been rehearsed. The procedures are not ready. In the final days, the question is raised. Do we fire the 5th burn or trust the plan? The room worries about the risk, the schedule, the lander arriving close behind. The maneuver is never commanded. 1 hour out, the number arrives one last time. 110 kilometers. The lowest pass this spacecraft can survive is about 80. 110 is above 80. Tight, but alive, the room breathes. What the room does not know is that the model has been lying for 9 months. September 23rd. The orbiter swings toward the far side of Mars for the insertion burn. Loss of signal is expected. It is part of the plan. The burn begins. 4 minutes and 6 seconds in, the tone cuts out. 49 seconds early. 49 seconds does not sound like much. To a navigator, it is a scream. It means the spacecraft is somewhere it should never have been. On the far side, Mars releases the sky. The moment comes for the signal to return. Silence. They call for hours. Nothing answers. The reconstruction finds the truth. The true pass was 57 kilometers, 23 below the floor. The orbiter met atmosphere it was never built to touch, and it was gone. The investigation takes 7 weeks. The world is told the story in one line. A metric mix-up. One team used imperial, one used metric. And everyone smiles because it sounds so small. But hold the file up to the light. The wrong units were survivable. The drift was visible. The doubts were spoken. The fix existed. A contingency burn that later analysis suggested could have saved the mission. NASA's own head of space science said it plainly. People make errors. The problem was not the error. It was the failure of the checks and balances to detect it. The units may have been the error, but they were never the cause. The cause was an organization where a warning could be heard, believed, and still change. Nothing. 10 weeks later, Mars Polar Lander reached Mars without its relay and was lost on the way down for reasons of its own. That file is still on the shelf. The orbiter's number was wrong for 286 days. Being right about it changed nothing, because being right had nowhere to go. Somewhere in your organization, right now, someone has a nagging feeling about a number. The question this case leaves behind is not whether they are right. It is whether your system gives them anywhere to take it.